Yes. Okay. So, good. Okay. So let me just go through the solution with you right away. Okay, and then I'll get it graded for you guys over the next few days. Okay. So this was a play on very simply, right? Power ratios, right? And it is, in fact, right, an example that you've seen before, probably sort of the aggregation of two examples. One is my hope, really three concepts I want to bring across in this. Okay, and we'll talk about what it is. Okay, so let me draw it out for you, because drawing it out for you, right, is probably the simplest, right, to sort of see how to approach this particular problem here. Okay, there's an easy way to solve this, and then there's a slightly more long-winded way of doing this. Okay, so what we have here, right, is a signal. Okay, that goes on a run, right, down a sort of a distance of 25 kilometers, right? So this is 25 kilometers. Okay, and then I tell you this. Okay, well, there's going to be a signal at P1, and then there's going to be a signal at P2. Where I tell you now, okay, well, at the end of the line, right, the signal at P2 is 5 watts. Okay. And my question for you is, okay, what is this signal at the beginning of the line? Where a couple of things happen. Okay? There is obviously within this line an attenuation of minus 2.5 dB per kilometer. Okay? But somewhere in this line, and I said, okay, in the middle of the line, I'm going to boost the power, right? And I'm going to add a value of here, right? 3.5. Right, and it's the boosting, so it's a plus 3.5. So there are a couple of things at play here, right? My question is really, what is P1 if I measure it at 5 watts at P2? Right, but along the way there are some losses, right, that I'm going to denote here in red, and then there's some gains which I'm going to denote here in blue.
Can I have a question really quick?
Yeah, go ahead.
I thought it was 2.5 decibels per 5 kilometers.
Oh no, you're right. Sorry.
Okay, I was like, oh no.
Yeah, sorry about that. Right, so there's a little 5 here per 5 kilometers. Okay. So in any case, there is a loss of and gain, right, throughout the system. Right. So a couple things I want you to be able to figure out, obviously, is okay. How do I find out what the total? Remember, right? The goal is to figure out, right, what this total path is in terms of gains or losses. Right. So if you're losing 2.5 dB per every 5 kilometers, how much do you lose in total? Chantel? Yeah, minus, exactly, right? So well, you basically, well, you say, okay, well, per 5, that's 5 times of this, right? Minus 12.5. Okay, so the total, the first thing to figure out is the total sort of gain or loss through this, right? So it will be like, okay, 5 times, right, minus 2.5, which is 12.5 plus 3.5, right, equals to minus 9 dB. So this is the one thing, is I want you to be able to figure out the total losses. I want you to be able to compute, right, by the addition and subtraction in dB. Okay. And then the next question is this. If this was 5 watts, what does minus 9 dB tell me? What is minus 9 dB? We reviewed this just moments ago. When I say that a system is at minus 9 dB, what does that mean? Is it triple? It's not triple, Rana, right? There's something more specific than that. Exactly, right? Which means, right, along the way, it lost half, and then it lost half. Right? Which means it is now at 1/8 the power. So really, P1, right, equals to 40 watts. So you could have solved it that way, and then you got into full marks. Okay? Or you could have used that to no, you don't have to round it. Okay? So then the next thing is, okay, if I didn't know that, how do I solve this? I know that I have a total of minus 9 dB, right? And I know that the power ratio goes 10 log 10 of P2, right? P2 over P1. Okay. And I know P2 is actually 5 watts. So my goal is to solve for P1. So to reverse the log, right, then you have a minus 0.9, right, equals to log of base 2 of 5 over P1, which means 5 over P1 equals to, anybody? So sort of without computing the answer, which you're right, okay, but I want to just sort of annotate this is not log base 2, this is log base 10, right? Yeah, sorry, my fault. So if you take 10 to the power of that, right? So you get 10 to the power of minus 0.9. Exactly. So then P1, right, equals to 5 divided by 10 to the minus 0.9. It's really difficult to write. Okay, which obviously is roughly 0.125, right? So 5 divided by that, right? You're going to get now, obviously, right, 39.7 watts. Is that clear? But there's sort of the easy way to sort of solve it, right? Because I, on purpose, made this, right, minus 9 dB. Okay, and your goal, obviously, right, was to figure that out, right? Do it just because you know that minus 9 dB is 1/8 the power. So at the beginning of it, right, should have been 40 watts, right? Or you could have gone through and solved based on the sort of the power ratios in dB. Okay, awesome. So I'll grade it, right, and then we'll go from there. Okay, that's fine. So that will be probably a small deduction. Okay, so you won't be perfect, right? Yeah, that's fine. It doesn't matter what the value is, right? It's an approximate value. Okay, Chantal. So either you reported it as value of 39.7, right, or you could have reported it as 40 watts. Okay. Any questions? Oh, why? So if you take 5 divided by 0.125, right, you will get. Okay, so you should be able to double check that. So this, no, but it should. No, but what did you get though, Chantal? Are you ways off, or are you? Oh, okay, yeah, okay, that's fine. That's fine. Okay, so as long as your calculation is done correctly, that's fine. Yeah, okay, yeah. So can I remind you, do not do rounding up in the middle of a calculation. You should only do your finance. And I'm not about rounding up or rounding down, right? The problem is that if you start to sort of take approximate values in the middle of a calculation, then those approximation actually amplifies, right, throughout the entire calculation. Okay, you should only do not rounding up or rounding down in the final answer, but you're trying to express it in 3 significant digits. Okay, so do not do, right, as best practice, and this is not just for this course, right? Best practice is do not round up or down in the best practice. Do not round up or down, right? I cannot. Do not round up or down in the middle of the calculation. Okay, Chantal? Do it only at the end, right? Just to express in the appropriate number of significant digits. Okay? Okay, so if yeah, so again, right, just do not round. It's not about being careful, right? It's best practice, right? Do not round up or down in the middle of a calculation. Carry the full value all the way through to the end. Okay, so let me view screen share, cancel this guy, right, and then obviously go back to this, right, and then back to this. Okay, who did some pre-reading of the material? I'm actually interested to know who did some pre-reading of the material. No, there will not be a midterm, but we're still unsure about the final exam. Okay, Lacey? Sure. Okay. So remember last week, right? We tried to motivate what we want to try to sort of cover in this material, right? So I can give you a bit more insight for next term. By default, it's online, but it doesn't have to be. Okay, so computing is probably going to be all online. No, there is no midterm for this online offering of the course. Okay, by default. So going forward, by default, it's online. I can think about putting one together. Okay, Chantal, but we'll do that as we get a little closer. But just so you know, right, the problems are continuously. You have lots of problems to do in terms of both practice problems from the textbook, right, as well as obviously, right, as the assignments. Have you guys done? Have you guys? Right. Okay, guys. Can we sort of not sort of discuss about sort of going forward yet? So as I said, the directives to us right now is by default, right? Just so you know, so students are going back to classes already, right? In programs where they cannot administer online, like I don't see some news articles with sort of the joinery sort of so like the carpentry courses where they have to actually physically work with machines and wood and the School of Nursing. Some of them under sort of guidelines provided by public health are actually back in class. Right, we are being told to assess whether or not as for every single course, right, by default will be online. But if there's a need to be in class, there are guidelines to follow as to how the classes will be held in class. Is that clear? Okay, so wait for the official announcements for your program, right, and not just sort of what some other sort of general statements are being made. Okay, so wait for program directives. Okay. Oh, okay. So I haven't received that email yet. So the email that I get is default online, and if it cannot be online or for whatever reason, then we will have to deal with that. Is that clear? Right, so by now the default's online, but there can be exceptions. Okay. 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 Thank you for sharing that with me. I don't have a copy of that email. The email that I get is directly from the institute, right? So you will get obviously program directives on a per program basis. So CIT, CST, full stack, but even other schools as well. Every program is making their own sort of assessment on how best to deliver for the fall. Right. Okay. No. So the question two, yes, we will not be going back. So what is happening is that we will not be pivoting online and in class at all. Right. So if it starts, if the course is already on one format, we will stay with the format for the entire term. Okay. The pivoting online and in class is actually very disruptive in terms of delivery. So there will be no change in the delivery at all, even if indeed that we're allowed to go back to classrooms if the class chose not to go online in the first place. Is that clear? Okay. I believe that there is no decisions made for winter of 2021, which means the term after. Okay. But in any case, can we get back to sort of the material here as we sort of work on because I want you guys to be work on the assignment. Okay, so as I was saying, right, why do we have to do digital transmission? Right, in particular the first case. The second case is very, very clear, right, that obviously if the signal's actually in so to read this, right, is the first point that we have here, right, this is digital as in the data. The second point here, right, digital to digital means digital transmission, right? The first point here is analog data and then digital transmission. So it's very clear, right? Okay, if something's in analog, like my human voice, for example, then if I want to send it, obviously, right, through some digital means, I actually have to do a conversion. And actually, that's a very fun thing to do. Okay, to give an example, right, anytime you've heard of like synthesized speech, right, it's effectively that's what it is. Okay, but what about digital to digital? Anyone? Why do we have, if the signal was already digital, why do we have to do digital to digital? Anyone? Does somebody want to unmute themselves? Rana, do you want to unmute yourselves? What do you mean by that, Zicheng? So you could be on the right track, but that's not the reason.
For it to be transformed, it needs to be turned into a signal and then back into a digital, maybe?
Sure, obviously. So the transformation has, if you convert something to a signal, you have to unconvert it, right? So we call a coded encoder decoder. Not quite. It's not that. It's not that, because at the end of this, right, whether it's MP3 or MP4, they're all ones and zeros. True. It doesn't really matter. It's just a different compression. One for audio only and one for video and plus audio, right? It's just a different standard of that. But they're still ultimately ones and zeros. What I'm saying is that if your data is really ones and zeros, then why do you need to find a digital signal to transmit it? Actually, you know this answer. You actually know this answer from 2721. So for everything that you do, right, you need to be able to obviously understand the very high levels why we're doing it, right? Not just sort of, okay, this is why we do it, this is how we do it, right? But really, the question, more important question is, why do we have to do this? Has anybody seen ones and zeros go through cables? Anybody seen ones and zeros go through a cable? No. Okay. The flashing light will be like fiber optics, right? But that's not digital transmission. Okay. What goes through a USB 3 cable? If you look at the cables that you have in front of you, and obviously there's data going through the cables that get connected to your laptop. What do you go? No, I'm talking about the actual transmission within the physical medium itself. Like, let's assume that you have some kind of a USB cable connected to your, exactly, voltage or current, right? In fact, right, you do know, right, that digital signals are transmitted, right? If I go back to this guy here, right, like this, right? This you have seen in 2721. Okay, and it's a terrible square wave, but this is what you see. Essentially, I'm saying this, right? There are discrete levels here, maybe at plus 5 volts. And then there's discrete levels here, right? Maybe at minus 5 volts. Right? Have you seen something like that? Right? And then I said, okay, well, if I have something like this, I could say that, okay, anything that's a high, right, it's a 1. Anything that's a low, right, it's a 0. And I keep going down that path. So the minimum of why we need to do digital to digital, right, and I'm trying to motivate this for you so you have an understanding of why we actually even do this, is because we cannot just transmit a logical 0 or logical 1. Yeah, digital to digital. No, the digital to digital just means data, right, and then signal. Okay, Shankai, it will be clear to you in a few slides. Okay, the digital means digital data to digital signal. Okay? And the reason why we have to do that is because we cannot transmit a logical 0. A logical 0, in fact, doesn't have to be 5 volts. A logical 1 doesn't have to be minus 5 volts. It can be any voltage I assign to it, as long as between you and I, we agree on what the voltage level should be. Okay, so in the early days, in sort of all the sort of voltages that we transmit, we have sort of 5 volts. We've gone from 5 volts to 3 volts. And then now I think we're down to about 1.3 volts and trying to go even lower, which means, right, your devices, right, tend to be able to last even longer. Okay. So let's take a look at why we actually do this, right, in terms of digital to digital. Okay. So before I can actually do that, I want to just reaffirm, right, sort of along the lines of what Shen Kai is asking, okay, the difference between data and signals. Okay, remember, right, the data is actually the information content. And the information content could be in a digital form or it could be an analog form, right? Example of information content in digital form would be like sort of things coming off your digital camera sensors. An example of sort of an analog data, right, would be like my human voice. Okay, so those are information contents. But when I transmit, right, I could transmit either in a digital sort of level, right, as a signal, right? This is a digital signal, or I could transmit in an analog signal. Okay. The first thing that we want to look at is transformation of digital data, right, which is the first digital here, using digital signals. And the simple argument is this, is that I cannot send a digital data, which is 1010 as a logical state, but I can send some voltage levels just to represent these logical states. Is that clear on why we actually do that? Any questions? Yeah. I'm trying to say this, right? I cannot transmit digital data. Digital data is really nothing but ones and zeros. True? Zisang? Right. It doesn't matter whether it's MP3. Those are just compression techniques, right? Whether it's MP3, MP4, but the data actually resides as logical states of ones and zeros. But I cannot transmit ones and zeros, so I use a digital signal, which is plus 5 volts and minus 5 volts to represent the ones and zeros. Okay? Inherently, because I cannot transmit states, but I can transmit voltages. Exactly. The voltages will represent the data that I want to transmit. But there's a lot more issues associated with that, right? Which is why we're going to look at different forms. Okay? So the first thing that we want to do, so this will be question 2 on your assignment 1. Assignment 2. Okay? You'll be drawing the different types of digital signals to do so. This whole process of doing digital to digital is actually called line coding. Okay? Is what we want to be able to do is to convert these digital data to digital signals. Okay? Can anyone hear me?
Welcome back.
Yeah, I can
thank
hear you.
Okay, no, I don't know why. Did anybody get get kicked out of Bongo?
No.
Oh, interesting. Hold on. Let me just reload my slides here. So, how much did you guys hear me? Did you guys hear me talk about the sort of line coding?
No. No.
Okay, let's just continue on with line coding here. Okay, do we get started? Do you guys hear me when I started on line coding?
Once you actually switch to the next slide, that's it.
Okay.
Everything.
Okay, that's fine. Okay, let's just continue from here again. Okay, so if somebody can sort of continue with the feedback, then I can at least hear you that you guys are still there. Okay, so the idea is this, right? Is that as I was talking to sort of Zisang, is that what I want to be able to do is, right, use some voltage levels to represent the logical states, because I cannot transmit the logical states of digital data, and hence we create the notion of having visual signals. So this process, right, in doing sort of digital to digital, digital data to digital signals, right, is a process called line coding. Okay, if we sort of look at, oops, I need to share the screen. If we look at sort of the diagrams, right, or what the sender and the receiver does is essentially this. I've created some digital data, and the representation of this digital data is essentially logical states, right? Really, if you start to think about what's a logical 0 and what's a logical 1, we as humans, right, think of it as either on or off. But that's not what a computer looks like, right? It's essentially 2 states, because I could create a 3-state system. True? In fact, I could create a 4-state system, like, and that's what quantum computing is all about. It does not necessarily have to be 2 states only. It is 2 states because we, at this point in time, right, we have what is called a binary system of on and off. But that's really just logical states. Now, if we have these logical states, we cannot transmit the 1s and 0s in this logical state. So what we need to be able to do is use this process of line coding and create a signal that I can actually put through the cables. Like, for example, your USB 3 cables. There are billions of 1s and 0s going through as the voltages change between a positive and a negative value. As I said, in the early days, right, your USB devices were on +5 volts and 0. Then they went down to +3 volts, right? And then now we're at probably 1.67 volts. And you start to see that they use less and less power. And obviously, right, they have longer and longer battery lives, and so on and so forth. But that's sort of enhancements, right, that we've done in sort of dealing with sort of the power management and the ability to detect signal levels. But irregardless what we do, we take this data that we have, which is really nothing but logical states, and then we convert it into a digital signal. We transmit that. What the receiver has to do, right, is to undo this process. So this is the process of encoder-decoder, where obviously, right, the receiver is going to now retrieve the same streams of 0, 1, 0, 1, right, and then send it up to the application. Is that clear what we're trying to do here? This whole process of line coding is looking at how we can use different representations, right, within this digital signal. Okay, and one of it would just simply be the voltage levels. It doesn't really matter what I use as long as I have an agreement, right, with the receiver. So if I'm trying to say, Zitang, I'm going to transmit to you 0 and 1s. Okay, a 0 is a negative voltage, a 1 is a positive voltage. That's not enough information really accurately for Zitang, because obviously we know that the voltage levels will fluctuate. But I can tell Zitang, if you receive anything between 0 and 1 volts, because I'm transmitting at -1.67, right? Or if you receive anything that's positive between 1 and 2 volts, right, because I'm transmitting at positive 1.67, then you measure the voltage, and then you will decode it as 1s and 0s, right? And I can specify that, okay? But before we go into the schemes, right, which is part of your assignment 2, question 1, okay, what I want to now do is a few more definitions, right? And these definitions are very specific, okay, and they're really precise. Okay, the first notion of it is what we call data elements. In your world, you call them bits, right? But you know, the formal name for it is actually called data elements. Okay, these data elements, right, and we'll use it very interchangeably with bits, are effectively what we need to transmit. So the 0s and 1s. These are the actual data bits. Okay, but as motivated, we cannot transmit these data elements, so we need to find signal elements. So the signals are what we can actually send. So in this case, instead of transmitting logical 1s and 0s, I'm transmitting +5 volts and -5 volts. If there are data elements and then there are signal elements, then obviously I need a measure for these data and signal elements. So with respect to time, right, the data elements are what we need to transmit. We call them the data rate, and we give it a symbol called n, right, which is the number of data elements we can transmit per every second. Does that make sense? So you're very well 1 gigabits per second, right, because you're transmitting some data elements 1 billion bits at a time and 1 billion bits per second. So that's your data rate. So if we have something like sort of data rate, then we should also have another quantity, right? And we call it actually the signaling rate. Okay, and it's the number of signal elements that we can transmit, right? Also in 1 second. So remember, right? Our unit of time, right, throughout the entire course is on a per second basis, right? And then we use metric prefix, right, to denote very large numbers, and obviously at the same time very small numbers. Okay. So now, if we have data elements, and then we have data rate, we have signal elements, and then we have signaling rate. Okay. Then what then we have, right, is we can redefine a new quantity called R, where R is the number of data elements carried by each signal element. Let's pause on that for a minute. What does that mean? How can you interpret R? First of all, directionally, do you want R to be a very large value, or do you want R to be a very small value?
Large value.
Exactly. Does everybody see that? If I define R to be n over s, in fact, I want R to be a very large value. So if you think back to for a few seconds ago, okay, and what I a few moments ago I defined this, right? Remember the road system that we keep talking about, right? The road system, okay. The road system is set up as such, right? We want the most lanes because the lanes represent the bandwidth. But let's assume, right, that the data elements are the humans. But what's really carrying the humans are the signal elements are actually the vehicles. So my goal really now is to say this. I want to pack the most number of humans. In fact, actually, it doesn't have to be humans, just passengers. It could be a dog, right? So I want the most number of passengers per vehicle that is driving down the street. And I want these vehicles to be as tightly packed as possible. So I really want R to be very large. But in fact, in practice, R is not really as large as we really want it to be. And I'll show you in a minute, because there are many other considerations, right? Look at it, right? Just like what they sort of encourage, which is called carpooling, and in these days they encourage van pooling, right? Because they want to say, right, per unit vehicle, we want the most number of passengers. Per unit signal, we want the most number of bits. Yet in practice, we don't always pack the cars to the maximum. Why? This is saying the last time you drive, did you have a full car of 4 passengers in your car? Probably not. Okay, so directionally, we all agree, yes, we should pack the maximum number of data elements, right, into each signal element. So we want R to be really, really large. That's ideal. But in practice, we cannot achieve that, right? So Zitang doesn't do that. Okay, but proportionally, right? You have to understand, right? Each human being is roughly about 150 pounds on average, right? I'm just saying, right? Just on average. Okay, but the car that you drive, Zitang, do you know that the car is at least 3,000 pounds? Are you aware of that? It's at least a ton. Exactly. So it is more efficient to carry more passengers per unit car, not because of the additional weight of the passengers, but because that car itself that you're driving, it's already about 3,000 pounds, right? And most of the energy expended, right, is actually moving the car, not moving you as a passenger. Okay, so directionally we want that, but we don't usually do that, and we'll get to the reasons why in a minute here. Okay, but let me motivate to you why we don't always have R to be a very large value. Okay. Yeah, exactly, the vehicle. Okay, so let me show you what it means by data element versus signal element, because you need to know this relationship, right? R equals n over s, where n is actually data rate and s is actually signaling rate. Okay, I should mention that the signaling rate, right, of the number of signal elements in 1 second is also known by units called baud, B-A-U-D. Okay, for those of you that were in the early days of dial-up modems, you might have seen things like 1200 baud modems, 2400 baud modems, not really bits per second. Okay, we equate that to bits per second because we assume that one bot is carrying 1 bit, and that's why it become equated to be bits per second. But in general, that does not have to be the case because in fact we want R to be large, which means more number of data elements per signal element. Okay, so if we take a look at this, right, this is R equals to 1. Why? Because there are two signal levels here. There's a negative signal level and there's a positive signal level. Very simply, right? This is what you saw in 2721. Okay, if you want to transmit the data element, which is 1 bit, right, of 1, use the negative voltage. If you want to transmit the logical value of 0, use the positive voltage, right, and so on and so on. So if I go low, high, low, right, it's 1, 0, 1. Okay, if I tell that to Zitang at the beginning of class, right, Zitang knows then obviously, right, this is how I'm transmitting to 1, 0, 1. Okay, let me show you a case where R is actually less than 1. Take a look at this diagram. What can you see about this? What can you say about it? Because you need to see what the difference is between the diagram on the left where R equals to 1 and the diagram on the right, which is R equals to 1/2. If you start to see the differences, then the question is, why do you think, and I can tell you in practice, we do R equals to 1/2 more than we do R equals to 1. And the question is why. So what is the difference? There is still a 0, right? There is a 0. You're crossing 0, right? Just as you would with R equals to 1. There is always a rising and falling edge, right? So the rising edge here, right, is at so the dotted lines here means bit boundary. So I'm going from bit 1, right, logical 1 to 0. Okay, so there is obviously a rising edge and a falling edge, right, and then a rising edge, right? There is one here too, right? This is 1 to 0. But now the rising and falling edges happen now in the middle of a bit. Okay, so if you start to see this, right, there's two couple things here to note. First of all, the logical 1 is mated to the negative voltage. The logical 0 is mated to the positive voltage. Everybody saw that, right, when R equals 1. That was a simple case. Now, if we look at this case here, we saw this, is that there are two voltage levels, right? A positive voltage and a negative voltage. But every data element is represented by 2 signal elements because they all either go from a high to a low or a low to a high. Does everybody see that? Okay, which means that I'm still using 2 levels. I still have a positive voltage and I also have a negative voltage, negative and a positive. But instead of using 1 voltage per logical sort of data element, I'm using two sort of voltage levels per each logical element. But in a 1, logical 1, I go from a high to a low. In a logical 0, I go from a low to a high. Does everybody see that? So in this case, right, first of all, you need to be able to read this, right? This is important. R equals to 1/2. Why is R equals to 1/2? Because now there is now 2 signal elements, a positive value and a negative value, to represent 1 bit. A negative value and a positive value to represent the other bit. So R equals to 1/2. Why do you think we do this?
My take is, in the first case, I'm actually measuring the voltage.
Yes.
And that's how I decide if it's a 1 or a 0.
Right.
In the second case, I'm measuring the shifts. So I'm looking at a shift rather than a voltage itself.
Exactly.
And that's how I know it's a 0 or a 1.
Right. But why? Why do I want to go through the trouble to do that? Because I'm saying that in practice, actually, this R equals to 1/2 is used more than R equals to 1. Why? Why do I want to measure the change? Not the shift, but the change. No, it's not because of that, Zitang, because the voltage not being stable is true, but it doesn't fluctuate that much, right? So let's assume I said that this is 5 volts and this is minus 5 volts. Yeah, it could go from anywhere from +4 to +6. Like it might fluctuate within that bound, but it's not going to fluctuate from a +5 to a -5. Right? Any other guesses in sort of your pre-readings at all? Why do you think we do this? One more guess. No. Obviously, right? Maintaining a constant voltage is easier. right? I'm still switching. It's just that one of them I'm switching in the middle of the bit. I don't see this is the logical bit one. I'm switching the voltages in the middle of the bit. The other one I'm switching at the bit boundary. So I'm still doing the switches, but now I have time shifted the switch, right, from the actual bit boundaries to the middle of the bits. It's not accuracy. That's not really the reason, because obviously, right, you're still going to get your +5 and -5, right, and you're going to perturbate between those values. The key here is this: you're changing in the middle of a bit and not at the bit boundary. Why? So we got 2 hours and 3 minutes left in this lecture. Should we pause here for 2 hours and 3 minutes? Or is somebody willing to share maybe another sort of idea as to why this is? A bit can manage 2 signal elements. I don't know what you really mean by that, but a bit is represented by 2 signal elements, not manage. And the question is why? So it's not a trivial answer, but the solution is really elegant. Okay, let me show you the other R values first. Okay, but they're not as important, right? So this is the case where R equals to 2. Right? R equals to 2 means that obviously, right, there's 2 data elements per level. So there's a positive and then there's a negative, right? I'm saying this: if you get a positive voltage, it's a 1, 1. If you get a negative voltage, it's a 0, 1. Right? And then obviously this is another one where it is a non sort of a binary sort of a change, right? Where it says this, right? I'm going to transmit 4 data elements using 3 signal elements, right? So this is 1, 1, 0, 1, represented by a high, which is positive, a negative, and a 0. So there are all kinds. I can create any of these, right? But what I want to really sort of be most highlighted to you is, why do we go from something less complex? Does everybody agree this is less complex? Because at every bit boundary, I'm just going to change my voltage, right? To something more complex, because I'm saying that I'm going to change now the voltage level in the middle of a bit. Right? Which means I'm trying to detect, right, the voltage change in the middle of a transmission.
Is it more changes can have more bits or more representations of bit sequence?
Not at all. In fact, R is half. Remember we motivated R should be high, right? R should be a very large value. We want R to be as large as possible, right? In this previous slide, we want to carry the most number of bits possible for every signal level. In fact, what we really want, right, out of all of these examples, right, if I give it a matter choice, which of these, right, should have the highest R value, right, and why, right? Because, well, you're using the least number of signal elements, the least number of cars to carry the maximum number of bits. So this is the case, right, where obviously a car is carrying 2 passengers. This is a case like Zitang, right, because he's carrying 1 passenger per car. Now, this, I don't know what this is, because this is like a car carrying half a passenger, right, which on average, which means every 2 cars, there's 1 passenger. Okay, so my motivation is this, is that I want, in fact, R to be large. We've expressed that. But in practice, in fact, I actually run R at a lower value. I shouldn't say a very low value, but a lower value. And the question is why? Okay, so it has got to do with synchronization. Okay, it has to do with synchronization. Okay, okay. So it's not about synchronizing between data elements and signal elements, but it's about synchronization between the sender and the receiver. Okay, so let me ask a question, right? Who in this class wears a watch? Anybody here wears a watch? Okay, good. Okay, so at least Ziseng and Shankai wears a watch. I'm hoping that they're both not sort of Android or Apple watches. Okay, like a traditional watch, right? Okay, Ziteng and Senkai, right? If you look at your clocks, right, which means your watches if you're wearing them, do you think the two of you are synchronized to the minute? in terms of timing? Like, are you all showing 11:02? Unlikely not, right? Which is, right? Probably not. Okay. Are you synchronized to the hour? I mean, should both of your clocks be at least 11 o'clock in the morning right now? Well, you should be, okay? But you're unlikely to be synchronized to the hour, right? That you both will agree. So if you're not synchronized to the hour, do you think you're synchronized to the minute? Do you think you're synchronized to the second? If I say that the class will start at 9, not 9 o'clock sharp, but 9 o'clock in the morning, 0 minutes, 8 seconds. Okay. So what type of data rates do you use, Zitang? The data rates that you use are in orders of what? Megabits? No. Data rates, like number of bits per second. Is it megabits, gigabits, right? Exactly. Okay. So you guys use very little data rate, right? Because I would expect you guys to come back and say, no, you use gigabits per second, but that's okay. Okay. If we have bits that are coming to us at megabits, which means millions of bits, true? And then if you push it to the limit, you are doing billions of bits at gigabits per second, true? What is the bit duration in megabits per second? How long does each bit last for? No. Megabits, inverse of megabits is, you know this, microseconds, exactly. Microseconds, okay? And then if you're going gigabits per second, then that's even nanoseconds, okay? So let me ask you a question. How many minutes have gone by since I was kicked out of Bongo? How many minutes have gone by, Zitang? Roughly, no, not exact. How many minutes? Like 3 or 4 minutes, okay? How many sort of seconds have gone by? Wonderful. Yeah, you multiply that by 60. Okay, so my question is, how many billions of nanoseconds? So how many nanoseconds have gone by? Do you know? No idea. Exactly. Okay. So if you start to think, the reason I give you these examples, right, is there's a real reason for that. Humans have sensitivity of time at most 2 seconds, which means we know an hour has gone by roughly because we can feel that, right? I mean, you guys can feel that, you know what, 2 hours of the class has gone by, right? 2 hours equates to about 120 minutes. That's a very long time because I can eat, 2 meals, right, or 3 meals or 4 meals in 2 hours. You guys probably have an idea of how many seconds have gone by roughly, right? Because you have that sensitivity to it. But you guys have no idea how many milliseconds have gone by or microseconds or it's not that you don't know how many of them, you can compute that, but you have no sensitivity, right, to time in that small of a resolution. Okay? I'll give you an idea. If you start to think that if Shankai and Zitang's watches are not synchronized, right? Maybe not even to the minute, definitely not to the second. If you're transmitting at gigabits per second, you're saying this, that the sender clock must be synchronized to the receiver clock at the nanosecond resolution. Is that a simple or a difficult task? Which means that you are precise in terms of your clocks to the 9th decimal place, right, for gigabits per second or nanoseconds. Very difficult, exactly. This is the reason why we would choose to run a system where R is a smaller value, because all of a sudden, this transition in the middle of a bit gives me, in fact, timing information. I could use this transition to indicate that that was the middle of my clock. And that is embedded timing information in the signal. And the cost of that, right, is obviously a lower R value, but I can use this lower R value for purposes of synchronizing the clocks between the sender and the receiver, which could be miles and thousands of kilometers apart. So I could have a sender, right, in Vancouver and then a receiver in Toronto. Okay, so the reason I spend so much time on this is that I want to explain to you is that, well, it seems very simple to say this. I can choose a scheme to represent ones and zeros, right, using the signaling, right? Because remember, at the end of the day, right, I'm trying to do something known as line coding, right? This is what I'm trying to achieve.
Could you repeat the last part, please? So
Yeah.
why are we using more than signal to represent one bit to actually be able to synchronize?
Right. I'm gonna go through an example of that for you later in a
Okay.
second, Rana. Okay, I will go through an example of that.
Okay, thanks.
Is because it is not as simple as just saying ones and zeros, because there are many other issues we need to deal with. Okay, we need to deal with things like clock synchronization. We need to sort of deal with things like, remember, right? No two clocks are exact. Certainly not down to the nanoseconds. But yet we need the timing of the clocks between the sender and receiver to be exact. True? Because if they're not exact, then I cannot decode the bits. I'm saying this, right? For you to figure out that this is a logical 0 and this is a logical 1, you need to now read this 0 in one nano of a second. And you need to be precise that, because if you have time shifted, then you're going to read something else. So in practice, right, we don't just have to sort of define the polarities, but we need to take care of things like clock synchronization, bandwidth, signaling, and so on and so forth. Okay, and what we really want to do, right, as part of what we can do, is that we need to find signals to represent the data, but we want to do so not just efficiently, which means R to be as large as possible, but we need to take care of the physical limitations and issues that we will encounter in the transmission of all of these signals. And because of that, right, we now have to look at different schemes in line coding to enable us to achieve that. Okay, so we'll take a 10-minute break here. Okay, and then come back, we'll go through all of these line coding schemes. Okay, is that good for everyone? We'll take a 10-minute break, right?
Yeah, sounds good.
And then we'll come back at 1118. Okay, and then we'll go through the different line coding schemes, highlighting the issues that we've just sort of discussed. Okay, so we'll resume in 10 minutes.
Hello?
여보세요?
네, 여보세요?
아유, 안녕하세요. 처음 뵙겠습니다. 저는 제주도지에 살고 있는 박원순이라고 해요.
네, 안녕하세요. 네? 아, 뭐, 잘 지내고 있죠. 네네. 죄송한데, 어디서 어떻게 저한테 전화를 하시게 된 거죠, 지금? 아, 아니요. 제가 좀 무교해서요. 네. 네.
Is everybody back?
네.
Is everybody waiting for the launch of SpaceX?
아, 죄송한데 혹시 이것만 간단하게 말씀해 주시겠어요? 제가 지금 미팅 중이어서.
Has anybody ever thought to train to become an astronaut?
아, 네, 알겠습니다. 네.
Yes, really? Karanvia, you want to be an astronaut? Yeah, so space travel is probably possible in our lifetime. I mean, your lifetime, I should say. Right? You might actually be able to at least travel out of Earth, right? And not just in an aircraft like an airplane, but you can go beyond, like the stratosphere or something like that, right? Like 30,000 kilometers up, into the air. Okay, go live on another planet for a year as a vacation and then come back, right? Okay. So it's 11:18. I'm going to continue on, right? So before the break, right, we were looking at exactly, okay, fully sustained life, in planet, Caribbean. Okay. So before the break, right, what we were trying to motivate was very simply this. Okay, we want to transmit some data, but because we cannot transmit the logical states of ones and zeros, we have to find a form of signaling to do so. Okay. Today we'll talk about everything that's got to do with digital signaling, which means I'm going to now use some put different voltages to represent that. Okay. And what does that mean? It means this. I need to come up with different schemes of representing it. But the idea of transmitting this, right, is not as simple because there are many other considerations other than a simple representation of using 0 as a minus v and a 1 for plus v. Right? Things like clock synchronization, bandwidth requirements, right, and so on and so forth. And we're now going to look into sort of the different schemes. This directly addresses question 2 on assignment 2. Okay, so by the end of today's lecture, you should be able to do questions 2, 3, and 4, right, and possibly an intro into 1. Okay, so my encouragement is that by the end of today's lecture, over the next week, do not wait for next Saturday to start working on the assignment. You should be able to do minimally questions 2, 3, and 4 to completion. Okay, and then we'll leave question 1 for post the lecture next week. Okay, so we're going to look at 3 different types of coding schemes. We're not looking at all of the different, and this is even not comprehensive, but we'll look at the sort of the 3 basics of it. Okay, what we call unipolar, polar, and bipolar. This really determines how many poles there are, which means how many values are used in terms of voltages to represent the signaling of the data that we want. And then more importantly, within these schemes, we're going to look at the different categories of return to 0 schemes versus non-return to 0, so the NRZ, the return to 0, right? To deal with what's called clock synchronization issues. And then obviously we're going to look at the bandwidth implications of these signals. Okay, so let's introduce you to them first, and then we'll talk about the pros and cons of each of these schemes. Okay, the most basic scheme is a unipolar scheme, which means there is only one pole, right? An example of which is something you've seen before. Plus 5 volts, right, for logical 1, right? 0 volts for logical 0. So 1, 0, 1, 1, 0 is represented by high, low, high, high, low, right? You probably have seen this. Now, the important thing to note out of this unipolar scheme, which obviously is the most simple scheme, right, is that it's unipolar, but it doesn't have to be plus V and 0. It could also be minus V and 0, which means I could flip this across the x-axis and goes minus V, 0, minus V, and then 0. That's also a valid, right? But what unipolar here means is that there's only one pole, right? Because there's only a positive voltage. Okay? Now, this is a non-return to 0 scheme, right? Because it doesn't change in the middle of a bit boundary, right? So this, right, scheme here that you see here, this is a return to 0 scheme because it actually crosses 0, right? Or it touches 0 in the middle of the bit. Okay, so this is a non-return to 0 because the signal does not return to 0 in the middle of the bit, right? So to read these timing diagrams, which you've seen before, right? These dotted lines always represents the logical bit boundaries. The voltage changes, right? If it doesn't change in the middle of a logical bit, it is an NRZ scheme. So it's a non-return to 0 scheme. Is that clear? Okay. So then the next type of scheme is called a polar scheme. Okay. So in a polar scheme, yeah, go ahead.
Just to confirm, so
yeah.
I'm using 1 voltage to represent 1 bit.
In this case, yes.
Okay.
So if you want to transmit 2 bits, you can still use like positive voltages, but you need to have 4 different voltages, right? Because you need to have 4 different. You need one level for 1, 1, 1, 0, 0, 1, and 0, 0.
Yes.
Okay. So all this is saying is this, right? In the most simplistic sense, right? This is a unipolar, but the unipolar can be positive V or negative V. Right? But more importantly, this is a non-return to 0 scheme because we are not dealing with clock synchronization. Okay? Which means, obviously, if the data rate is very low, you will start to see, right? Unipolar schemes are fine. NRZ schemes are fine. Okay? So in polar schemes, right, is where we now have the idea of going from positive voltages to negative voltages because it's a polar. So be very clear, it's not bipolar, polar. Polar has 2 poles. Bipolar has 3 poles. So be very careful with the terminology. Okay? So in this case, right, you're going to range now from positive V to negative V. Okay? Which is what it says here. The voltage levels are on both sides of the time axis. Okay? But notice that there's 2 schemes here, what we call NRZ, because it's still a non-return to 0, right? There's no transition in the middle of the bit. Okay? So it's NRZ L for NRZ level and NRZ invert. Okay? So let's focus on NRZ L first. Simply, it's the same thing, right, as your unipolar, but now I'm taking advantage of the negative pole. So I go from 0, 1, 0, 0, 1, 1, 1, 0. So I go from high, low, high, high, low, 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 high. Right? So we've seen this. It's just that instead of going to 0, we're crossing, right, the 0 and go from plus V to minus V. Okay? Now, let's take a look at this invert scheme. Okay? Where by definition it just says this, right? The change or lack of change in the voltage level determines the bit value. So for example, if I'm going to now go 0, 1, 0, 0, 1, 1, 1, 0, same as before, I go high, low, 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 high, low, high, high. So take a look at the moment of the scheme for now. Okay, and obviously that's the definition, right? It says that if the next bit is 0, then you do not do inversion. If the next bit is a 1, you do some inversions. Okay, what can you see out of the scheme? That is a trend of the scheme.
The
I'll give you
actual oh,
Yeah, go ahead. Go ahead.
the actual two signs, they're actually like a reverse of each other.
What do you mean?
So like NR ZI,
Yeah.
if you flip it around,
Yeah.
it's actually the exact same pattern, just flipped along the x-axis.
I don't quite get you on that one. Why do you say that they're flipped on the axis? Yeah, if I flip it, and what happens?
They're almost identical because, like, you know how it has the 111
Yeah.
on the right side? You've got
Yeah.
the 111 or the 3 low
Yeah.
on the left side.
Oh, I see. So you say that if I flip it, I will still get the similar pattern to it.
Very similar, yeah.
Oh, I see. Okay. Okay, but that's not so maybe that's probably an observation, but not the intended purpose of this NRZ invert scheme. I want to give you a hint though. Focus on the values of 1 between the data and the signal values. What can you say about that? No, good observation, Chantal. But it is not the intent. So it could be a byproduct of this scheme, right? But it's not the intent as to why this scheme exists. Is that clear, Chantal? So there's nothing wrong with that. It's an observation, which is good. Okay, it's just that it's not the intention of the scheme. But I want you to focus now. Look at the logical ones and their associated signal levels. What can you see for this?
In the NRZL, if the voltage changes, there may be an error, a misreading of the bit, whereas in the NRZI, there is no change in the voltage. So the no change can be actually interpreted as a 1.
No, not quite. Not quite. In fact, it's the reverse of that. Look at the associated voltage levels for each subsequent logical ones. What can you say about that? Sure, if it's not a 1, it holds steady, but what can you tell? Okay, so what is the voltage for the first one? Exactly. Does everybody see that? The first voltage of 1 is negative, the next voltage of 1 is positive, the next voltage of 1 is negative, and the next voltage of 1 is positive. Does everybody see that? Anytime there's an occurrence of a 1, in fact, that the voltage actually changes polarity? Does everybody see that? And that's the intended consequence of such a scheme. And the question is why? And I could have done a scheme that just causes the zeros to alternate in voltages as well. It doesn't have to be 1. But in this case, right, this depiction of it shows that I'm intentionally actually changing the polarities. Okay. This is actually a phenomenon called baseline wandering, or sometimes known as DC wandering. Okay. Why is that the case? I'll tell you why. Okay, let's assume, right, I have a long stream of bits, okay, and I'm holding the value, right, like NRZL. Whether it's polar or unipolar doesn't really matter. Okay, now let's assume now I'm computing the averages of the long stream of bits, which means, right, if I have a bit sequence, right, that goes high, low, high, high, low. Okay, just simply we just go back to sort of unipolar. Right, and do this. If I'm computing the average of the values that I'm getting, and I'll tell you why I'm creating the value, computing the average. What happens to the average if I have a long string of 1s? Versus if I have a long string of 0s. And a long string, I really mean like a billion entries, right? Because remember, you're transmitting at gigabits per second. What do you think happens to the average if I have a long string of 1s? Does the average skew towards V or 0 if you have a long string of 1?
V.
Yeah. Does the average skew towards 0 if you have a long string of 0s?
Yeah.
Okay. And this is the problem. And you might know, well, why is that a problem? I'll tell you why this is a problem. So remember, right, we said this, right? We're defining the voltage levels to be between 0 and V, right? If you're logical 1, you're a 1, you're at plus V. If you're logical 0, you're at 0 volts. But in reality, right, we need to create a threshold, right? Because the V is not going to hold at plus V. It's going to now degrade from plus V to maybe plus V minus something, which is a delta. As long as it doesn't, let's assume that we decide that the midline, right, which is V over 2, right, is the threshold. If you're above V over 2, you're 1. If you're below V over 2, you're 0. But in practice, right, the impairments on the channel does not necessarily, right, cut the threshold, right, and set it at the halfway point. There might be more impairments on the higher voltages and less impairments on the lower voltages, which means, in fact, I could go and create this, right, as V, right, over 3, for example, as the threshold. So I can cut the voltage really, really low. So in practice, right, what happens is this. The receiver actually doesn't just blindly say, okay, I'm going to use the threshold to be the midway point between V and 0, which is V over 2. But I'm going to now, based on the average values I get over a long string of 1s and 0s, determine what these values should be. So what do? I measure the average. So I take, okay, of all the values that are coming in that is representing V, right, at the receiver, I'm going to measure whatever the voltage is. All the values that are 0, I'm going to add this to, I'm going to take the average. So the midpoint may not be exactly a V over 2. But the problem is this. If I get a long string of 1s, and it's very easy to get a long string of 1s because you're doing it big gigabits per second. So a billion bits coming in at plus V, right away your average skews to V. So what's the purpose of NRZ invert schemes? Very simply this. It is to ensure that that long strings of an intended bit value, like 1s, for example, right, will always get the average to be the middle of their received values. So you're trying to find out what the threshold actually is. Is that clear? Of what I'm trying to say here? Is that because you don't always divide the threshold at the midway point, but you're computing based on the polarities actually received at the receiver. So a way to find out what the threshold is to force a change in the polarity of the signals, and then getting the average of those values, and then set that as your appropriate midpoint. And this is what the invert schemes, as an intention, attempts to do. Okay? Any questions on that? Yes, Zishan. So like, you can get better threshold than RCL. That's right. Exactly. It's not that it can get a better threshold because you're dealing with sort of the cases where there are long strings of 1s and 0s coming, and then that skews the average. As I said, if you have a billion of 1s coming, right, it's going to skew towards plus V. If you have a long string of 0s coming, you're going to skew towards minus V. But if I enforce, right, the 1s coming in, right, to always alternate between the high value and the low value, I can get a better reading, right, and a better average of what the actual voltage threshold should be. Is that clear, Zitai? Exactly. So it's a not dramatically, it's dynamically adjusted based on the actual received values. And this thing, right, in the textbook, right, it's called baseline wandering, right? If you're looking at, or sometimes also known as DC wandering. Okay, if you're interested in start taking a look at it, right? And I'll give you a summary of all of these in a minute. Okay, I want to just go through all the phenomena. The next thing that I want to talk about, right, is obviously what I talk about the clock synchronization that we alluded to. Remember, right, if I want to now transmit this string of bits, and obviously this is a polar scheme, right? This is a polar level scheme because all the 1s are held at high, all the lows are held at 0. Okay, so if I alternate between 1s and 0s, 1 0 1 1 0 0 0 1, right? And you know about clocks, right? let's assume, right, that the receiver clock is a little faster. So these are the clock boundaries, right? This is a clock for bit 1, this is a clock, and so on and so forth. Let's assume the clock's a little faster. Okay. Now, if it's a little faster, now it's going to poll in the middle of the bit, and oh, this is a 1. In the middle of my bit is still a 1 because I'm still within this range. So all of a sudden, right, I'm now going to read out a lot more bits because my clock is a little faster. So when the sender intended to send 1011 0001, I receive a much longer string of bits like 110 111 000011 and so on and so forth. Okay. What I'm going to skip this for a second here, right? What this signaling allows us to do is this, is that I'm going to now cause and force a change in the middle of a bit. Okay, and this is what I mean by clock synchronization issues, right? Is that if I force a change, I now know that that's the middle of your bit, which means, right, because there is no change here. But if I force a change here, I know that this is the middle of your bit. I can realign my clock to the middle of your bit. Does everybody understand that? Right? I can sort of illustrate that a little, hopefully a little better for you. Right? Is that, let's assume that I have in the sender, right, a clock that looks like this. Oops, I need to get a pen on. Right? Okay. Right. This is my bit boundaries. Right. Okay. Let's assume now I can draw sort of a signal and I have a change in the middle of a bit. So I do this. Right? Doesn't matter what it is, but there's always a change in the middle of the bit. Yeah, does everybody see that? Now, at the receiver clock, let's assume I'm a little faster. So I can draw a line here, right? I'm a little faster here, right? And I'm a little faster here, right? And so on and so forth, right? So my clocks are a little smaller. Okay. So really what happens is this, is that your clock, right, is here. The middle of your bit is here. Right, the middle of your bit is here. Right, the middle of your bit is here. This is not drawn to scale. Does everybody follow? But my middle of the bit, right? My middle bit is here. My middle of the bit is here. My middle of the bit is here. Right? I can figure out what this delta is. This is the delta. And they're all constant values, just so you should know, right? Because they're digital clocks. If I can realign, because I know that every time there's a transition in your clock, which is here, right? If I can figure out these deltas, then I can realign my clock to your clock. Meaning that, okay, I know that this is the middle of your bit. I'm now going to now shift my middle to your middle, right? Because I know what this delta is. So then I'll be polling, right, your values here in the middle of where your signal levels are, because I reshifted my clock. Does everybody get the illustration that I'm trying to do here? Any feedback from anyone? Hello? Is there anybody there? Yeah.
I need to do some reading.
Yeah, okay. So the idea is that because your clock could be shifted with respect to mine. And I said, no clocks are exact. So this timing information, okay? And obviously I'm going into a lot more detail than you really should be responsible for. But the idea is this, is that if I'm shifted in time, because my middle of the bit is here, I'm going to poll, you're here. My middle of the bit is here, I'm going to poll, right, you're here. I'm going to now end up reading more bits. And the problem with this is that this is a very, very, a problem that increases in its issue as the bit rates go up. Right? I'll give you an example why that is the case. If I say this, right, I have a digital transmission, and the receiver clock is around 0.1%, 0.1%, not even 1%, 0.1% faster than the sender clock. Okay, on a per second basis, we're trying to figure out how many extra bits are actually being read. If the data rate is 1 kilobits per second versus 1 megabits per second, right? So if I go at 1 kilobits per second, okay, well, every sort of second I read 1 extra bit. That's probably not an issue. It's still an issue because that's still incorrect. But if I go to megabits per second, I'm reading 1,000 extra bits per second. Now, the rates we transmit now at are gigabits per second, which means every second that goes by, I'm going to read an extra 1 million bits. Is 1 million bits a lot of bits? Just extrapolate the value for a while, right? Is 1 million bits a lot of bits? 1 million bits represents, right? If you're using 8-bit characters, that many more characters. Okay, so because this is such a important issue, right? We now have to correct for that, and the way we correct for that is by changing the R value. Okay, and what that simply means is this: is that I'm now willing to go and transmit less bits per signal levels, which means R equals to 1/2, because I'm going to effect a change in the middle of the bit, as with all these schemes. Okay, so you can either touch 0, like the return to 0 scheme. Okay, so low to 0, high to 0, low to 0, low to 0, high to 0. Right? I could do this, which is a level scheme, or I could do a polar scheme, right? Which means I'm cutting through 0, like Manchester. Right? So I go from high to a low, right, for a 0, high to a low for a 0, high to a low to a 0, and then low to a high for a 1, low to a high for a 1. Okay. But obviously, right, I also have the DC wandering issue. So I could also go with a differential Manchester, right, that is a invert scheme, where there's always an inversion, always in the middle of the bit, and then the boundary inversions depend what the next bit is. So if I now say this, right, the next bit is a 1, there's no inversion. So I go from something to 0. So if I'm a high, because it's a 0, I'm going to invert. I'm going to go down to a low. But in the middle bit, because the return to 0 scheme, I have to invert back up. Because the next bit is a 1, right? There's no inversion. I'm going to hold on to my high value here. My high value here must transition a bit to a low value. And the next bit is a 0, so I must invert. I'm going to go from a low to a high first. But again, in the middle bit, I'm going to have to transition back down. The cost of this, right, is simply bandwidth, because there's more signal levels, which means more cars are required to carry data elements. And really, right, that's the type of phenomena that we're trying to deal with. And if you just sort of sit back for a minute and appreciate this, right, sending a signal through a USB cable is not as simple as what you saw in 2721, which is, okay, if it's a logical 1, let's use 5 volts. If it's a logical 0, let's use 0 volts. Okay, there are things such as baseline wandering that we need to deal with. There are things such as clock synchronization that we have to actually deal with. Okay, another example of sort of the clock synchronization schemes, right, are ones called AMI. AMI just says alternate mark inversion, which means alternate the ones. Mark means 1. Pseudo ternary means alternate the 0. So in this case, you'll see that every consecutive 1 changes in polarity. So this is a high, this is a low. In pseudo ternary, every consecutive 0 changes in polarity. High, low, low. Right? So you get a choice of whether you want to switch on 0, right? I mean, alternate on 0, or you want to alternate on 1, depending on the bit stream that you expect to receive, right, in your transmission. Okay? So to sort of summarize on all these line coding schemes, and you will actually draw 4 of these in your assignment too. It's actually quite fun, but then the drawing actually allows you to appreciate and understand a little deeper. Okay? The idea behind it is actually very, very simple. I'll give you a summary in a minute. You do not need to memorize any of these schemes, even for the final exam. Okay, there's no need for you to sort of memorize these schemes. But you need to understand the issue and the resolution for it. Okay, so what do I mean by that? Okay, let me just go back to my slide mode here. Okay, there are 3 things that we want to deal with here. Okay, there are 3 things that we intended to deal with here. Okay, there is the issue of polarity. Right? Okay, and what are those 3 poles that we deal with? Anybody remember? How do we deal with polarity? As I said, you do not need to memorize any of these schemes. I'll sort of describe them to you, but you need to know at a very high level what it means. Okay, in polarity, right, we have unipolar, we have polar, and then we have bipolar. Unipolar just means there's one polar. Polar means there's two poles, positive and negative, right? And then of course bipolar means that there is positive and negative and zero. Okay. Then we have to deal with something known as baseline wandering, right? Or DC wandering. And how do we deal with that? Does anybody remember? We use the notion of invert schemes, where depending, right, on consecutive ones or zeros, we flip the polarity of it. Okay, and then the third thing that we deal with, right, is what we call clock synchronization. Right? How do we deal with it? We use return to zero schemes versus non-return to zero. Okay, so you don't have to memorize the schemes as, okay, draw me a unipolar RZ, and so on. You don't have to do that. You don't have to memorize whether it's positive to a negative or negative to a positive. But what you're responsible for, right, is you need to know this categorization, right, of all the different phenomena that we're trying to deal with and how we actually deal with it. From a polarity point of view, where there's unipolar, there's polar, and then there's bipolar. Okay. From a BC wandering or a baseline wandering issue, we use invert schemes. Yeah, which means subsequent ones or subsequent zeros should change in polarity. And then so this is the second issue you want to deal with. And then the third issue you want to do, which is clock synchronization, right? You want to deal with what is known as a return to zero scheme. Is that clear? Any questions on that? And obviously, right, the cost is the more signaling, right? So the cost really comes down to your R value, right? Where R equals to N over S. Okay, that's important, right? Because your signaling increase, right, equates in more bandwidth being expended because more cars are used. Is that clear? So no need to memorize any of these schemes, right? You don't have to memorize any of these. I'll explain them to you if I want you to draw something, okay? But what's important, oops, I should show you this, right? You don't have to memorize any of these schemes, okay? But what's really important, right, is that you actually know this distinction of the issues we're trying to solve. Polarity, baseline, and clock synchronization. Okay? Is that clear? Any questions? Exactly. That's all. That's what I want you to know. What solves what, and what are the issues associated? So what are the issues? The three issues that we talk about: polarity, baseline, and clock synchronization, and the techniques to solve it, and then the cost of solving it. Okay, Z-time? Okay. Does anybody else have any questions? Okay, so I want to cover now the last section in this module, right? Which is really, really fun because you do this every day, okay? It is called analog to digital conversion, right? Also commonly known as something called pulse code modulation. Okay, what is this? Well, it's simply going from analog to digital. Why do you do it every day? Because most of you every day, right, you use some kind of a mobile device, right? A digital mobile device, right? So that would be the likes of your tablets, that would be the likes of your mobile phones, right? Anytime you're using a voice-activated command where your source is now analog, right? And what you transmit is actually digital, that's an A to D. Okay, so this is commonly known as A to D. Okay. Every time you speak to a digital mic, this happens. Okay, so the question is this, right? How do you think we can represent analog data using digital signals? What do you think? How do you think we can actually do that? Who's actually converted analog music to some MP3 format, some digital format? Anybody has done that? Has anybody done that? Anybody know that there has been a lot of conversions of analog audio, which is obviously captured in an analog format, to a digital format? Chantel, have you done any of those? Have you actually sort of converted analog data to digital before? Or Rana, have you ever done that before? No, nobody. Okay, so are you guys all digital? Is that what your generation is all about? Every music piece that you get, audio piece that you get is all digital. Oh, okay. So I grew up in a generation where we have actually cassette tapes. Have you guys seen cassette tapes before? Yeah, so exactly. So I actually had cassette tapes. We moved out of it, and go on to CDs. Creating a catalog of CDs was once sort of an important thing, like how people would collect sports cards and stuff like that, right? Exactly. Okay, and then obviously then it went on to sort of like digital formats and MP3. But there's a strong pushback now for LPs, right? Like a lot of people are buying LPs again, right? There's something about sort of the fidelity. Okay, and we'll talk about what fidelity is. When you convert from analog to digital, you will lose some fidelity. It's a representation because it's a conversion, okay? But you do not get back the exact same quality. Okay, so let's take a look at this. Okay, so the most common use case for this, right, is your modern day cell phone. Right? Every time you talk to it, right, there's a conversion of analog data, which is a human voice, right, to some digital signals. Okay, so let's go through the high-level process first, right, of what this really is. Okay, supposedly, right, I want to capture, right, the yawn of Chantel. Okay, the yawn of Chantel comes on in like this, right? So if Chantel was to yawn, right, she's going to go high and then come low and then, stretch it out for a few minutes here. Okay, my goal, right, is to create a representation of Chantel's yawn. This process or this technique that we're going to go through called PCM, right, or pulse code modulation, right, has 3 sub-processes associated within the encoder. It goes through some sampling, then it goes through some level of quantization, and then it goes through some level of encoding. At the end of the day, we'll go through these in a minute, right? At the end of the day, right, what I'm trying to get at is this digital representation of Chantel's yawn. Okay, so are you comfortable in producing a yawn, Chantel? Can you produce a yawn for us? I don't know if she's still online. Is anybody comfortable producing a yawn? Just audio, over the microphone?
Is everyone?
Now read this.
Rana, can you produce a yawn?
Oh, I don't even know how to do that. So maybe someone else this time.
Okay, so there's a nomination for a person called Jason. Jason, where are you? I've just made Jason the presenter. All right. Okay. So Jason, I want you to prepare to make a yawn in a few minutes, okay? Because you're not even logged in microphone mode. So I'm gonna let you change into a microphone mode. There's a nomination by Melody to have you do a yawn. Okay. So apparently, it may be because you do that quite a bit during classes. I don't know. But Melody probably knows better than I do. Okay. But let's think about this process for a second here, right? I have a analog signal that's coming in, right, Jason? So I want you to be ready to produce a yawn in a few seconds if you can. Okay. The question is this: how do you think I can actually represent this digitally? If you have ever heard of any of the early days of Sound Blaster Pros where there's digitized voice, right? It sounds very, actually I cannot produce that, but if you ever watch things like, the Terminators, right? They have obviously like a very roboticized type of a voice, that's actually being produced, very discretized. Okay, but human voice, which is analog, right, is actually very, very fluid, which means there is a smooth change in tones and there's a smooth change in frequencies. There's a smooth change in amplitude, which is what this represents here. If this is time, right, this is Jason's yawn, and he's practicing his yawn right now, right? He's in microphone mode, muted for the minute. Jason, are you ready to produce a yawn? There we go. Can you produce an exaggerated yawn so we can all hear you?
An exaggerated yawn.
Yeah, which means extended over time, like take 10 seconds to do it.
Okay. Are you ready?
I'm always ready.
Okay, fine. Oh.
Okay, there we go. Okay.
Yeah.
So I do that for a purpose, right? Supposedly I want to capture that digitally and have a accurate reproduction of that yawn. How do you think I can actually do that? How do you think I can actually do that? Well, the PCM process says that we have to go through 3 different sub-processes. The first thing is that I need to sample it. Okay. What sampling means simply says this. Okay, so this is the PAM signal I want to create. This, obviously, all the x-axis is time. I'm going to go through, as Jason is making that yawn, capture his yawn, right, at fixed intervals, fixed times intervals. And every time I capture something, I'm going to record down the amplitude that I capture. So does everybody see that this is Jason's yawn based on this analog signal that he produced? Okay. But obviously, right, it's not a smooth curve because I did not capture every point in between, but I captured only the points at these fixed intervals. But if I join up these points, which means I'm interpolating his yawn, I could get something reproduced like this. Does everybody follow that? Okay. So then the next thing that I need to do, because I want to produce a digital output, then I'm going to go through a process called quantization, which means this, right? These values that I've captured, these values that I've captured here, they're all real values. So this could be like plus 4 volts, plus 4.5 volts, plus 6 volts, plus 6.8 volts, and then plus 5 volts, and so on and so forth. But that's not a digital value. So what I want to be able to do and say, okay, if I've captured that, right, what I want to be able to do now is that I'm going to break down all of these values that I've captured, right, which is the values that you see here. And then I'm going to now assign them to one of 8 levels as shown here. So the first value, which was as plus 4 volts, right, is now going to be level 1, 2, 3, right, or 0 starting from 2 starting from 0, right? So 0, 1, 2, 0, 1, 2, 3, 4, right, and so on and so forth. So this will be a level 2, this will be a level 4, right? This will be a level 6, right? This is also a level 6, even though there are different heights. But in any case, we'll talk about how the details of all these processes in a minute. But my goal is very simple, right? First of all, I need to find time to capture the signal. Then I need to now assign these captured values, which are real valued values, which means they're like, 4.4, 4.1 volts, 4.5 volts, 5.3, and so on and so forth. And I'm going to assign them to a digital level. Okay? And then finally, right, I'm going to represent these digital levels as a string of 1s and 0s. And that's what PCM is all about. So, are there any inaccuracies at this stage when I'm capturing at certain time points? Any inaccuracies? How can I improve on the quality of the signal I capture? Anyone? How do I improve? Chantel or Rana or Jason? How? Yeah.
Taking more samples in a smaller time frames.
Exactly. So imagine, right? I'm taking, I say, oh, I'm going to choose a time interval to capture this. Right? I'm going to use the time interval to capture this, right? But my goal is this, right? Is that I want to be able to capture more details, because if I want to capture all the changes going on in here, I just have to reduce the time between each capturing of the time points, true? Right, just what Rana said, I just have to increase. So in order to get an exact reproduction of this analog signal, well, then I should capture an infinite number of points. Does everybody agree? Because if I want to capture all of the changes to this analog signal, then I just have to capture at every time point possible, which means I'm going to now capture an infinite number of samples, right, to reproduce this analog signal. Same thing here, right? If I want to go and say, I want to give and say this, right? Remember I said this is level 6 and this is level 6, but they're actually different amplitude levels. In order for me to have a very accurate, distinct value for each of these quantized values, then what I need to do is I need to have an infinite number of levels, because this is a continuous function, right? This changes minutely over time. Okay, so I would need then obviously also an infinite number of levels, which means if I want to reproduce this analog signal accurately, I'm going to produce an infinite number of data bits because I have to get an infinite number of data points, and I'm going to have an infinite number of levels. So what we have, obviously, right, is never, right, an exact reproduction of analog. Okay, and if you wonder why, because the world is inherently analog, right, and it will always be inherently analog, right? I mean, can you imagine, right, driving on a car with where the car has only square wheels, right? That would be a difficult ride, okay, and somewhat terrible. So we're going to now go through sort of the process, right, in a bit more detail, and talk about the things that we need to do at each of these sub-processes, right, and the trade-off that happens, right, as we go through this process of creating this analog signal in digital format. And what obviously we don't have is that we don't have the luxury of being able to create an infinite number of data bits, because we cannot capture infinite time points, and we cannot have an infinite number of data levels because we cannot transmit an infinite bit rate. Okay, so the first thing is sampling. Okay, and I'm going to use the whiteboard to show you what I'm trying to do first. Okay, so let's assume, right, this is the yawn of Jason. Okay, this is the yawn of Jason, right? And obviously this is with respect to time. Okay. So think about this. Okay, if I'm going to capture this, right, the first thing that I said was, okay, the first process we have to do is called sampling. Number one, sampling. I'm going to now, at certain time points, capture Jason's yawn, which means every time I sample, I'm going to get this dot here, and I'm going to get this dot here, and I'm going to get this dot here, and then I'm going to get this dot here. Okay, so this is sampling. So if I were to join these lines together, right, I mean, I kind of get this reproduction, but it's just not as smooth. So you start to see, right, if I want to get more and more of these data points, then I really should sample more. I should maybe sample here, I should sample here, so I get a smoother curve. Does everybody see that? Right, and I can keep cutting it, right, and say, okay, I want to sample here, and again get these values here, right, sample here, and so on, so on, right. So I'm going to remove those for now. Okay, so assuming that I'm doing this type of sampling, right, this is what the question is: how many samples should I take? Right, we know that the more the better, but more should not be infinity, and we'll talk about how we actually sort of restrict ourselves to do so. Okay. Now, the second, does anybody remember what the second process is?
Quantization.
Exactly. It's called quantization. What is that? Well, it's about breaking this into different levels. Let's assume that I do a very crude quantization, right? I'm going to get two levels. So this is a 0, and then this is a 1. So Jason's yawn. Jason, can you do this yawn again? Are you there, Jason? Oh no, he changed back to mic only. No, Jason, I need you to be on microphone for your main, because I'm going to get you to reproduce that yawn all the way through. Okay, so we'll give him a few seconds to come back online. Okay, so when Jason created his yawn, it was varying frequencies and amplitudes. Right, and he did a very sort of accurate reproduction of that. Okay, he was able to do so in a way that would, did this change and so on and so forth. Okay, we'll give him a few seconds. He's going to get back online. Right, I almost wish there's a one-click, like audio. And actually, I don't even know why you guys want to go on microphone mode only. Obviously, I'm imposing on Jason, but I hope he's at least waking up, because I want to demonstrate something very quickly once he does a yawn. Okay, so if you unmute yourself, Jason. Okay, you can do a yawn now.
The same one?
Yeah, the same one. Just like follow this. Yeah, go up and then down.
Oh.
Okay. Can everybody remember that for a second? He did a beautiful yawn. Okay? But if I were to quantize it to just 2 levels, which means that there's only 2 discrete states in his yawn. So he went from a high to a low and so on and so forth. If I were to quantize it to 2 levels, then if I were to reproduce, which means that this amplitude and this amplitude is the same, this amplitude and this amplitude is the same, because this will be represented by 0, this will be represented by 1. His yawn is now going to sound like this. Ba, 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 ba. Does everybody get that? Because I got 4 points, right? If I'm going to play this as a tone, right, it's going to go ba, 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 ba. Does everybody get that? Jason, can you do your yawn again?
Sure. Oh.
Does everybody hear that my reproduction of his ba, 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 ba is absolutely not the same? And it's not about not enough points, it's saying there is not enough quantization levels. How do I make sure that his tones are even more accurately reproduced? Well, I can say this. I don't want these two because they're really not the same value, right? This value here is really not the same value as this. So what I could go on and say is this. Okay, let's quantize it even more. Does everybody see what I'm doing here?
Yes.
Then I can say this now, that this is now 0, 0, 0, 1, 1, 0, 1, 1. Then all of a sudden, even with the same sampling, I'm going to get a bit more fidelity to his yawn, because now it's going to sound like ba, 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 ba. Does everybody get that?
Yes.
Because then I have 4 but I have 4 different representations of it, right? Instead of ba, 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 ba. But now I have more levels. I can go ba, 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 ba. And obviously, right, the more levels I have, the more samples that I have, the more alike I'm going to sound like Jason. And the question now is, obviously, is, right, one, how many samples should I take? How many quantization levels do I do? This is actually the whole PCM process. And then at the end of the day, the digital reproduction of this is very simply this. Let's assume that I decided on this sampling rate and then this quantization levels. Then this point is going to be denoted by simply, right, if I find a proper color here, 1, 1. This is 1, 0. This is 0, 0. And then this is 0, 1. So what's transmitted at this level of quantization, at this level of sampling, right, are the bit streams 1, 1, 1, 0, 0, 0, 0, 1. This is our best effort depiction of Jason's voice. Is that clear? Of what we're trying to do here. I haven't gone through the details. I've just given you an illustration what we're trying to do, right, and how we're trying to obtain what is known as PCM. It is a grid, and it will become a grid in a second here. Okay, so a couple of terminologies since we're on this diagram here. So if I have a sampling rate, right, and I'm going to now call it f of s, right? F of s is my sampling rate. Is the number of samples I take per second. Okay, let's assume now that this is 1 second here. What's the sampling rate here?
4.
4, exactly, right? So I'm taking 4 hertz. What is this duration between each of these samples? 1/4, right? Because we know, right, that T of S, right, this is called the symbol duration. The T of S equals to 1/f of S. Right? That hasn't changed. Does everybody remember that? Right? F is inversely proportional to T. What is the resulting bit rate of this system?
8 per second.
8 bits per second, right?
Yes.
Why? Because we're taking 4 samples per second, and each sample is 2. So the third process here is called encoding, right? And what we now have, right, is this, is that the data rate is none other than f of s times nb, which is the number of bits. So 2 bits per sample, right? 4 samples per second. This is 8 bits per second. Does everybody see that? So then really, right, we have just gone from Jason's wonderful, glorious yawn that Chantel labeled it as, right, and reproduced it in the most crude form as an 8 bits per second system. And obviously, right, the higher the bit rate. So you might have seen when you were doing sort of ripping CDs into MP3s, right, you might have seen things like, oh, okay, what is the sampling rate that you want? Oh, what is the quantization levels that you want? Effectively, you are tuning the system to get a more accurate reproduction of the system. Okay, so we'll take a 10-minute break here. Okay, come back, we'll go through the deck of slides, right, that will help us illustrate this in a lot more detail, right? And the big questions now really, right, is to answer the 3 questions is, how many samples should I take per second? How many quantization levels should I have, right? And how do I encode this final signal? Right? And that will form the basis for you to do questions 3 and 4 for assignment 2. Okay, so we'll take a 10-minute break here, right? 10-minute break. Break. Okay. Oh. Do you guys want to watch the launch? Is that what it is? Melody? Yeah. So should we go for another 10 minutes and then take the break in 10 minutes? Shall we do that? Are you guys okay with that? I'm fine with that if you guys want to do that.
I just have a question, if possible.
Yeah.
Are there any maybe YouTube clips or something like that that you would recommend us watching just to understand the first section, the color schemes and all these things?
The what scheme? Sorry. Oh, you mean like the line coding schemes?
Yes.
Oh, I'm
if
sure
I could get more than maybe, I don't know. I'm definitely going to read the book, but maybe if I could even, if you could recommend some other resources, that would be great as well, just to have a better understanding.
Right. So Rana, just send me an email, okay? Because I don't have a list of videos for you to watch. I can search for you and show, okay, I can quickly review some of the clips and then say, okay, this is a good one to actually review.
Perfect.
Okay. If you do that, then I have a follow-up action item to work on. I just don't have a list of because I very rarely use somebody else's video. But I'm sure if you require that, so the first thing you should do is obviously read the book. Okay. The second thing, obviously, right, is to send me an email, and I'll look for it, and then I'll find 1 or 2 that I think has close resemblance to sort of the material we're teaching, right? So a lot of directiveness on that, right? And then obviously higher quality videos. Okay.
Perfect. Thank you.
Okay. So let's just go for 10 more minutes because Melody wants to watch the launch. What time is the launch, Melody? 12:20, is it? What it is? 12:20? What's the launch time? Yeah. Okay, 12:20. Okay, so let's cover up sampling and then we'll let you guys do that. Okay. So the first thing that we need to do is sample, right? As I said, right? The more samples we take, if I can take another sample here, or I can take another sample here, or I can take another sample here, well, the better the reproduction. But the problem is this, I cannot sample infinitely. Because if I do sample infinitely, the consequence of it is that it will result in an infinite number of bits. Does everybody get that? So Nyquist, do you guys remember Nyquist? So we have Shannon's and then we have Nyquist. Nyquist simply says this, we need to sample at least twice the highest frequency component. Think for that for a minute. It says this, right? If I have a signal and we know there's a bandwidth, right? There's a bandwidth, which means there's an F low and an F high. The minimum you should sample at is at least at twice the highest frequency component. That's what Nyquist said. And the question is why? Why? Let me give you a hint. If a signal is very slow changing, do you need to capture more samples or less samples?
Less.
Right. Let's just do the extreme case. If the signal is never changing. Okay, let's assume that I'm making a tone, right, Rana? I make a tone. Bang. Melody, how many samples of that tone that I just produced do you need to sample at so that you know how to reproduce that? I think she's watching CNN already. Exactly. So if I'm making a tone that's not really changing like this, how many times do you have to capture that to be able to reproduce it? How many times do you have to hear it to know what tone I'm producing? Sampling just means this, right? You're shutting down your ears, right? And you're trying to make a capture of a signal going by. Right? If I go ba, right, and I want you to reproduce that. Really? One. Isn't that true? All you need is just one capture, because you need to know the amplitude and you need to know the frequency. So what I'm trying to say is this: if something is not varying at all, in fact, you can get by with just one simple. If something is static, which means it's not changing, you only need to capture it once, and then you can reproduce that. Okay, but if something is fast changing, let's assume, right, that I'm talking really, really fast and I'm talking lots of data, right? And I'm going da 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 and keep going on. If I want you to reproduce that, how many times do you have to capture that run?
Lots of times.
A lot of times.
Number,
You have to capture. Basically, you want to capture every change that exists. True. You want to capture every change because in order for you to accurately reproduce that, right, you have to capture every change in what I just produced. It's highly, highly dynamic. So sampling simply says this, right? Michael says, you just have to minimally sample at twice the highest frequency. Okay? Twice the highest frequency just simply says this. You want to get at least 2 samples of the fastest varying signal. And if you can do that, right, then you have a very high accurate, right, reproduction, right, to capture the signal. Okay? So I'll show you some examples of what it means by that, right? And we'll take a 10-minute break here, right? Because I know you guys want to go and watch the launch, right? So we'll have a 10-minute break here, and we'll resume right around 12:27. Okay.
Sounds good.
Yeah, thank you, guys.
Come on, but yo,
Okay, is everybody back?
Yeah, I'm back.
Okay. Did everybody watch the launch or? Okay, can we continue yet or? So it's really nice. It's well, so far still a successful launch, right? So that's really good. But I thought that was did you guys see that there was a time differential between the actual launch and the takeoff? As I don't know which channel you're watching it from, but from where I was watching on the news channel CNN, it launched before time t equals 0. Right, for some. Oh, I see. Okay. So maybe that was a more accurate, maybe there's some delayed start to it. Okay. So let's hope for a successful launch. Is this your first launch you guys are watching for the first time? Probably, right? Because you guys are probably about 18 years old or so, roughly. Okay. Awesome. Okay, so let's continue on with this, okay? You got to obviously always appreciate the engineering that went into all of this, whether it's, you know, launching of satellites, communications, right? It doesn't really matter. Okay. So I want to sort of continue back with this, right? And sort of give you guys an idea of what it means to sample at Nyquist, okay? So before the break, right, if you guys are all back from watching the launch, okay, we said this. There are 3 processes, and I intend to go through the 3 processes before the end of the day today. Is that the first thing we need to do is sampling. Then the next thing that we do is actually quantization. And then the third thing that we do is actually encoding, right? Sort of how we go from an analog signal, right, to its actual intended bit stream, okay? So as I said, if a signal is very fast varying, then you want to capture it more. But if a signal is completely static and not changing at all, then the capturing of one signal point is probably sufficient. Okay? So Nyquist came back and it told us this, okay? We need to sample minimally at twice the highest frequency component. Okay? It doesn't matter whether or not the signal is a low pass signal or a band pass signal, you're always trying to find Fmax, not bandwidth. Right, Fmax, because bandwidth is Fmax minus Fmin, or F high minus F low. Irregardless of whether it's actually sort of a low pass signal or a band pass signal, I want to sample at twice the highest frequency. Let's see some examples of that. Okay, let's take a look at this sine wave. Okay, and in this particular sine wave, right, I'm sampling at the Nyquist rate. Okay, does everybody see that? Okay, so if I were to go this sine wave and I choose my data points, right, and because there's about 2 sine waves here, right, 1, 2, okay, I'm sampling roughly about 5 points, which is double the frequency of the sine wave, right? So there's 2 hertz being shown here. I'm taking about roughly 5 data points. If I join these data points, does everybody see that I very much kind of approximate this original signal? Does everybody see that?
Yep.
Okay. Now, what happens if I do twice the Nyquist rate, which means I'm now going to take, instead of just 5 points, but I'm going to double that. I'm going to take 10 points now. And if I join all of these points together, does everybody see that now I get more or less the same diagram as with only sampling at Nyquist?
Yes.
Okay, which means oversampling really didn't, this is what we call an oversampled case. Doesn't really gain me that much more information, especially for a well-behaved signal. But let's take a look at what if we don't sample at Nyquist sampling rate. Okay, if we take a look at this and I say now, okay, I'm now going to go at half the Nyquist rate. So I'm now, instead of sort of less than half, I should say, right, is that instead of taking the points that is at least double, if I take these data points and I connect them, does everybody see that this does not represent this original signal? And not only that, it actually gave me the wrong plot. And this is a phenomenon what we call aliasing. Is that you're not only losing information, but you're getting the wrong information about the signal completely. Because this, obviously, right, is in no representation to this. Okay, and it's based on all of these sort of empirical studies, right? The Nyquist came back and said, okay, well, the minimum that we need to do, right, is to capture at least twice the highest frequency. because we want at least 2 data points of the fastest varying signal component in that signal. Any questions on that before I give you another example? Any question?
Clear enough.
So the next thing that we say, right, let's take a look at a clock. Okay, so for most of you, right, you may have seen only digital clocks, but let's assume that there is an analog clock, right? Now, sampling just means open and closing your eyes, right, at the moment of time, right, to look at the things that you're supposed to see. Okay, what we have here now, okay, if you sort of see here is that I'm going to now sample at the Nyquist rate, right? And if I focus on what's called the second hand, which means that it completes, right, 1 revolution in 60 seconds. If I want to double the frequency in terms of sampling, I'm going to do it once every 30 seconds. So if you scan from left to right on this diagram here, can you see that the clock is actually moving? Can you see that the clock's actually moving? If you go from left to right.
Yes.
Now, if I sample, right, above Nyquist rate, what difference do you see if you scan from left to right?
I know for a fact it's going forward.
Exactly. Whereas in this previous case, you don't actually see that.
Could be
Right?
backward.
You-
Yeah.
Yeah, you know that the clock is moving, but you don't know exactly whether the clock's moving forward or backwards. But if I oversample, I'm going to gain a little bit more information because now I'm going to capture them, right, at twice Nyquist, which means I'm doing it every 15 seconds. Now, if I open and close my eyes every 15 seconds and I see this, then I see that the clock's actually moving forward. But what if I undersample? See, I do it once every 45 seconds. What do you think happens?
Looks as if it was moving backward.
Exactly. Who watches fast action movies? Anybody here watches fast action movies? Like, I don't know, like the Need for Speed or Fast and Furious, like Clint Eastwood movies, right, where you have lots of tires spin. Many times when you see a tire spin in a television set, do you realize that the wheels are actually spinning backwards? If you ever recall like a chase, like a fast chasing scene, right? Most of the times you actually see that the wheels are spinning backwards when the car is actually moving forward. Why do you think that's the case? Why? Why is it that
Undersampling?
it's what's undersampling what? So first of all, right, the wheels are spinning, I don't know, I mean, your tachometer may show 8,000 RPM, but your wheels must be spinning at, hundreds, right, RPM. Exactly. The videos are usually captured, right, in a movie, right, 24 frames per second, sometimes 60 frames per second. So in fact, you're undersampling because the wheels are spinning maybe 600 revolutions per second.
So less frames than it should be, or
That's
something
what,
like
sorry?
that.
That's what,
Less
sorry?
frames. Less frames.
Exactly. So you, in order for you to get an accurate reproduction of it, you need to sample at twice the resolution, right? In terms of the frequency, right, in relation to the wheel speed. So the question is, what about your eyes? What is the response time of your eyes? Does anybody know? Anybody here has done a biology degree before? What about your eyes? Is what you're seeing really what is happening, or are your eyes deceiving you due to the lack of sampling?
I'm guessing it's deceiving. It's just because I know it as a fun fact. Sometimes the eyes compensate.
That's for vision, but I'm talking about sort of the sampling. If something is really, really fast moving, do you think your eyes can capture it at its full fidelity, meaning that if it's moving forward, and you're not seeking? No, helicopter blades, right? Usually you're seeing that in television or in person. In person, right? So do you see the blades spinning backwards? Okay, so what is the limit of human eye then? I'm going to leave that for you to find out. There is a limit actually in terms of sampling, okay, for the human eye. Okay, but in any case, right, what I want to do is wrap up on sampling, right? The first rule of thumb, right, is that in your f of s, you must do f of s equals to 2 times f max. Okay? So then the next question is this. Okay, if I have a low pass signal and it's at 200 kilohertz, what's the minimum sampling rate I require for this signal? Anyone?
200 minus 0 is 200 times 2, 400.
400,000. Okay. What if I have a band pass signal? So not a low pass. What about a band pass?
Well, I need to know the first frequency, right?
Exactly, the low frequency. And in this
Yeah.
case, you do not know, and therefore you cannot figure it out. Okay, so it's not just about doubling of the frequency in terms of bandwidth. It's about doubling of the highest frequency component, which means even if you're just given the bandwidth, you need to know what f min is to add the 200K to. Okay, so now let's spend some time on quantization, because this is the slightly more interesting thing that you need to do. Okay, so remember, right? When I quantize, my goal is to get an accurate reproduction of what these values are. Remember, when I first started off with sort of a 1-bit system, I got ba, 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 ba. And then when I went to a 2-bit system, I went ba, 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 right? And obviously, if I want to get an even more accurate reproduction of it, right, I would have to keep increasing the number of levels. Okay? So I'm going to use the next slide to highlight that. Because let me see if I can overlay on this. Well, I can't, because I cannot erase anything. So the thing that I want to sort of show you here is this. Okay, let's assume if I have 2 sample points here. Okay, but you can see it, probably another sample point here. And I'm saying that, okay, I have the values, right? This is 0, right? And then this is 1. Does everybody see that, in fact, this value is not this value? Does everybody see that? They actually have different values, but I'm estimating them, approximating them to be the same value. Does everybody see that?
Yes.
Okay, and that's what quantization is all about. Okay, what do you think is wrong with this? What do you think is wrong with this? Because I'm saying, right, is that let's assume that I have a 0 and 1, okay? And I said this guy and this guy is estimated the same, whether in actuality they're not. What I'm introducing here is known as an approximation error. Okay, and what is this approximation error? I'm saying this, right, is that all of these points I'm estimating, in fact, to the middle of the level. So this is the middle of the level 1, which means this particular sample here, I have introduced an epsilon 1, because I'm saying this point is actually here. This point also has an epsilon because it's not dead on the line, but I'm estimating this point to be here. So there's an epsilon 2 associated with it. How do you think I can reduce all of these errors to 0? How do you think I can reduce all of these errors to 0? Anyone? Infinite quantization level, exactly. So what I really want to do, right, is to go in and say this, okay, I'm now going to break all of these points, right, even more. Break it even more. Such that at some point, all of these sample points fall on these. Which means, right, if I use n equals to 1 bit, I'm going to get 2 levels out of it, L equals to 2. If I use n equals to 2 bits, so I'm going to get 0, 0, right? 0, 1, 1, 0, 1, 1. Right? I'm going to get L equals to 4. Does everybody see that? Corresponding to the number of bits you're using for quantization. Right? Remember this guy here? Right? The more bits that I use, the resulting of a higher bit rate. So to get around this issue of quantization, let's take a look at this particular example here. Is that if I say this, right, that I captured all of these levels as minus 6.1, 7.5, 16.2, 19.7, 11, 5, and so on and so forth. And I say that I'm going to break all of these levels down into just 8 levels. 1, 2, 3, 4, 5, 6, 7, 8. I'm going to now rename them as quantization levels 0, 1, 2, 3, all the way through to 7, where these levels equate to the middle of each of these horizontal bins, right? The middle, right? So quantization level is the middle here. Because why? If you take a look at all these, right? All of these fall uniquely into one bin. But this too, even though in reality, the original signal was created with the value of 16.2 and 19.7, I'm saying that they are now both quantization code number 7. So I'm actually introducing an error to say that they're actually the same. In order for me to eliminate this error or to reduce the error, then I need to double. So this is a 3-bit system. I could go to a 4-bit system and it will break this down by half. Then these two will be at 2 different levels. Does everybody see that? Does everybody see that?
Yes.
Okay. So how do you read this chart? Very simply, right? It says this. Okay. If I'm going to now say this, right? I'm sampling between -4 delta. So I have 8 of these levels. And I'm spacing out between the values of -20 volts and 20 volts. Each of these has a range of 5 volts. Does everybody see that? Because the total range is 40 volts. There's 8 levels. And therefore, each of these has a range of 5 volts. If I were to normalize these actual PAM values, the actual 6.1, 7.5, I need to divide all of these values by 5. This is what I get for the first row. Minus 1.22 because minus 6.1 divided by 5, 7.5 divided by 5, right? 16.2 divided by so on and so forth. These, in fact, tell me that, okay, based on this new quantized levels, this is at position -1 because it's 1 bin plus 0.22. This is at plus 1.5 because it's 1 bin in the positive range plus half a bin here. This is 1, 2, 3, 3.24. This is now 3.94. This is what this normalized PAM values are. But because all of these quantization levels are with reference to the middle of the level, the estimation of all of these, so you're saying this minus 6.1, right, which is at minus 1.22, is estimated as minus 1.5. 1.5 is 1.5, 3.24 is 3.5, 3.94 is also 3.5, and so on and so forth. So this third column here, this third row here, sorry, is the error that are introduced to all of these quantizations, which means what I really want is for this normalized error to be 0. But obviously, we know that if I want to have the normalized error to be 0, then I would need, as Zi Chang said, an infinite number of levels. Sorry, Shankai. And obviously, that's not doable. Okay? So I'm always going to have errors. And the question now is this. If I know that, right, f of s, right, must be at 2 times f max, right? So in terms of sampling, f of s must be at 2 times f max. Then the question is, how do I do quantization? Well, it turns out, right, there is a rule of thumb we can actually follow. Okay? We can say this. Okay, I know now that I've requantized this. I know that this is not perfect. But at least I've got a quantization, right? Because I've introduced some errors. And I'm going to say this first point is now quantization code 2 because it's 0, 1, 2, right? So no, that's a difference. The quantization code is the actual assignment of levels. The encoder words is nothing but the binary representation of the code. So this is 0, 0, 0, this is 0, 0, 1, this is 0, 1, 0. So depending on which level you fall within each of these 8 bins, you assign a quantization code, and you encode it into binary as a binary representation of the quantization code. Right? So at the end of the day, right, this is the bit stream that you're transmitting, but with errors. And the error introduced is because of the approximation. Does everybody follow that? Does everybody follow that? Okay, so how do we estimate that? It turns out that it says this. Okay, we can determine the amount of error, right, in relation to the quantization by defining SNRQ to be approximately 6 NB. So let me write that down for you here. Okay, forget about the correction, but I'm saying this, right? SNRQ, right, is approximately 6 times MB. And this unit is in dB. Okay, what this means is this, is that, remember, right, NB is the number of bits. If NB equals to 1, L equals to 2. If NB equals to 2, L equals to 4, and so on and so forth. So we know that the more bits that we use, the better it is. But it says this, is that every time you add 1 bit, because you have NB equals to 1, 2, and so on and so forth, you're increasing your signal-to-noise ratio. But in this case, the quantizing signal-to-noise ratio by 6 dB. 6 dB is how many times improvement? Does everybody see that as 4 times? Because every 3 dB is doubling. Effectively, what this is saying is this, is that for every NB that I add to the system, okay, I am halving, obviously, the gaps, but I'm reducing the amount of errors by 4 times. So this is an equation given to you, right? Whether that's minus 1.25 or plus 1.76, right? That's just a correction factor of 3 dB. But the basis behind it is that every time you add more bits to represent each level, you're doubling the number of levels, and you are decreasing the approximation error by 4 times. Okay, and so if we talk about sort of how to solve this, right, your sampling obviously is determined by 2 times Fmax, right? Your quantization, right, is approximately 6 MB. So let's take a look how we actually use this. So if I say this, right, there's a telephone line, right, and it must have a quantizing signal-to-noise ratio of no less than 40 dB. No less than 40 dB. Then the question is, what is the minimum number of bits per sample? On your own, I want you to take a minute to do this. It's really just applying SNRQ equals to 6 MB minus 1.25. How many bits do you need per sample if you want an SNRQ of no less than 40 dB? Anyone? How do we compute this? Well, the guideline that we have, right, is that it must be, obviously, SNRQ, right, equals to 6 MB minus 1, but must be greater than 40 dB. When we compute that, we get 6.875. But remember, right, we must have a quantizing ratio of no less than 40 dB. So we cannot go below 40 dB. So we must be at least 7 bits per sample. Does everybody follow? Yes, Chantel. So this, you don't take the floor, you take the ceiling. No, because it's the ceiling, because it says no less than. If I take 6 and I go 6 times 6 minus 1.25, what do I get? A value greater or lower than 40 dB? Right, if it's no greater than that, we go down. right? Because this is no less than 40, right? We have to go 6 times 7 to give us 42, minus 1.25 gives us 40.75. So it's at least no less than that. So usually, right, you assign 7 to 8 bits per sample in the transmission as part of a human voice transmission. Okay, Chantal? Okay, and then to wrap it up, really, right? Then at the end of the day, right, the bit rate as we demoed, oops, I should have shown this. The bit rate that as we've demoed, right, simply is just the number of sample points. No, bits must be integer values, so it must be 6. Okay, then if we go back, right, to sort of the previous slide that we showed, right, in this sort of example, right, is that to obtain the bit rate is really nothing but fs times nb. So it gives us the third summary point, right, where now when you do encoding, right, it's really fs times nb, and in bits per second. And that's really it to sampling, right? It is so widely used that I really want you guys to be aware of how sort of PCM actually works, right? Because you do it every day, okay? And the consideration is this. If my goal, right, is to reproduce the digital representation of this analog signal, I need to sample minimally at twice the highest frequency of the component. I need to quantize meeting, right, SNRQ equals to 6 MB. And then the resulting bit rate will be something I can reproduce, right? What does that mean? So if I take a look, and this you're not responsible for, what the receiver does, it simply says this, right? If I get a string of 1s and 0s, the first thing I would do with these 1s and 0s is obviously create this, what we call a staircase signal, because that's what it is, the discrete levels. Then I would need to smooth it out to obtain the analog signal. This analog signal will be a true reproduction of the original sending signal if 2 conditions are met. Number 1, we sample at or greater than the Nyquist sampling. Not guaranteed though, but a very high probability of reproducing it. Okay, and obviously, right, sampling it is not sufficient because we need to quantize enough, which means obviously I need to have created enough quantization levels. If I can satisfy these 2 requirements, right, one is your NFS and one is your MB, then I can recreate this original signal, right, with a high level of reproduction. And that's what PCM is all about. Okay, so to sort of summarize, right, I want to pull up the assignment 2 for you guys. Okay. So there's 4 questions to your assignment 2. Okay. So as I said, this is due now June 10th, right? Which is another 2 more, at least another lecture after this, right? But it's not the Monday, but the following Wednesday. Okay. There's 4 questions to it. The first question you cannot do yet. Okay. This is the part where we will deal with analog transmission. But question 2, right, is simply going through the different schemes and drawing this bit sequence. Question 3, right, is a question, right, to determine, right, the bandwidth, right, for something known as frequency division multiplexing. That you cannot quite do yet, but it's actually very easy to figure out. We'll cover that. Okay. And then question 4, right, is a PCM question. So it's a composite signal, right? You get different frequencies in each of these composite signals. Your goal is to be able to reproduce this analog and determine what the output of this analog is in digital form. Okay, is that clear on what this assignment, the questions on this assignment? Okay, so you should be able to work on half of this, right, which is question 2 and 4. Okay, just not question 1 and 3, right? Because this covers the D to D, and this covers the A to D that we covered today. Okay, please make an attempt to do it, right? Read the questions for 1 and 3 as well, so that if there are any questions, I can address it next week in the lecture.
In the next quiz, what should we expect?
Oh, all the way up to 4.24. All the way up to the end of today's lecture. So your next week's quiz, right, will cover everything on digital transmission. Right, so all the way up to this slide here, 4.24. So all of D2D and all of A2D.
Yeah.
Okay.
Okay.
So that's really sort of the end of the lecture for today, right? I'll stay behind for another minute or two, right? If you guys are still watching, I don't know if Melody's still watching the launch, right? But in any case, please have a great weekend, right? Please start doing the assignment, okay? Please start doing the assignment. Don't wait till next Sunday to work on it, okay? You can do half the assignment already, okay? So please proceed with that. Okay, the launch was quite interesting though, but I did see a time lapse version of it, which means that there was a bit of a time that did not match up to the T-minus countdown, right? So in any case, thank you everybody. Okay, so I'll stay behind for a few more minutes. Right.
In terms of recording the upcoming lectures, any decision have been made on this one or not yet?
No, so